I'll use the blackboard. And before we start off, because I unfortunately only arrived today, so I don't know you guys yet, so I want to just do a little poll. So who of you would say, I'm a physicist? So who's a physicist? Okay, excellent. Who's a computer scientist? Yes, one person. Who's a mathematician? You can show up multiple times if you want. Who's an engineer? Okay, excellent. So, are there any other species? What are you? You are? A chemist, excellent. No biologist? No. Okay, excellent. So the overwhelming majority of physicists. I'll try to adapt. This is great. So do ask questions, especially also the ones who didn't show up their hand for physicists. You don't feel embarrassed. Just ask questions if you don't understand what I'm saying or if something is unclear. You should just interrupt me. We should have enough time. I want to tell you about multi-particle entanglement. And I think Fernando already told you lots about entanglement. And where is he? Is he gone? Here. Okay. He told you lots about entanglement already. And there'll be some connections. And since I didn't attend your talk, just throw in and hands up and say, oh, look, this is connected to that, etc. The mathematical background or the mathematical theme of this will be the connection of multi-particle entanglement to tensors. And I'll tell you what tensors are, and then we'll connect it to some very old computer sciencey theme on algebraic complexity. I'll connect it a little bit to that, and I think maybe looking at the schedule for the summer school, there will also be a number of connections to the talks by Matthias Treuer and Frank Verstraete on matrix product 6. For the ones interested in that, I can also highlight more. So do come to me and ask me, could you say more about that or less about that? Do like that. So there is some material I'll mostly focus on, and it's contained two reference papers. I wanna just give you the archive numbers too. And those are this number 1208 0365. That is called entanglement polytopes. Entanglement polytopes. I'll speak about that. I might get to it today, later, or tomorrow. And the other one is 1709 07 851, and this is called, it's a more obscure title, maybe it's called Universal Spectral Points. So we'll maybe discover what that is and how it's connected to entanglement. All right. This year is joint work with Michael Walter and David Groß and Grant Doran, and this is more recent stuff together with Jeroen Zoutdam and Peter Franer. All right, good. So that's sort of like the reference, and so I'm trying to give you some background. All right, here we go. The lectures are structured into three parts. The first part is a very brief introduction, and after that we come to the two main parts. One is understanding kind of like one copy of entanglement, one copy entanglement, and then in the second theme is an asymptotic analysis. So you can think of if you want to, so basically after the introduction I have a part A, which I will call a single copy analysis. So if you, and then the second one here, that would be multi-copy. So you could just to give some intuition to these words here, the first would correspond if you think in the realm of data compression, then a single copy analysis would be, I get a single file, let me try to compress it, and a multi-copy analysis would be, imagine I get many copies of that file, or many copies that I want to compress, then how can I do that better? So we'll be interested in like some kind of single copy and multi-copy analysis, and so that will be the rough structure of my talks on tensors. But what are tensors, or what is multi-particle entanglement? Let me start with that. So I'm wasting a lot of space, it seems. Well, okay, we'll erase it later. Start in the middle. Okay. So here are three vector spaces in a-dimensional space C. Okay, so these are just vectors with a numbers in them, a complex numbers, and we're going to tensor this together with a vector space, complex vector space of dimension B, and a complex vector space of dimension C. Okay, and you can think of an element in here. I'll call an element in here a tensor, and so that thing is going to be called a tensor. But for all the physicists in the room, and most of you, this is of course just a quantum state of three particles, where this particle has dimension a-dimensional particle, a b-dimensional particle, a c-dimensional particle. You can think of them as spin particles. But A, B, and C will be finite. So if you want to think of a harmonic oscillator, you can truncate it somewhere, and have this three particles sitting in here. And I say tensor at this point because in quantum mechanics we have these. So when I just talk about the vector spaces here, I don't have an inner product on them yet. Okay, so in quantum mechanics, the first axioms of quantum mechanics say, well, let there be a Hilbert space, right? And a Hilbert space is a complex vector space with an inner product. And if I don't really care about the inner product, then it's just a complex vector space. And if T is an element in here and I don't care about the inner product, then people typically call it a tensor. And then later, but you might just give it an additional inner product, and then you might call it a quantum state. And for the rest of my lectures, and you will also see why, we don't really care about the length of it. We don't really care about the fact that it's normalized or not. We'll just try to understand the structure of the quantum states or of the tensors in this vector space. All right. Well, there's a natural thing to do. A natural thing to do when you have a vector spaces like this is to give yourself a basis and write out T in the spaces. So let me, for this space A, give a basis, and that's the basis just has a 1 at the ith position and has zeros everywhere else. That's the basis for that vector space CA, and I can give myself the basis for the B and for the C in the same way. And then, of course, the tensor producting them together, I will get a tensor product basis. We typically call it the computational basis for this tensor product vector space. Now I'm not using very much the bracket notation here, but of course you might think of this here just as the cat I, right? In that space A, and we could also do that. I'm kind of choosing to run along with this notation, and then if things are unclear, I will try to explain. And so I have a basis, so I expand my T in this basis, and then T will look like Tij,k. These are just some complex numbers, and the sums here run over I from 1 to A, right, and J from 1 to B, and K runs from 1 to C. Many. Good. All right, so here are some examples. Okay, so what's the simplest example we could, so maybe one thing I should say is that of course Tijk, this is an array, a three-dimensional array of numbers, three-dimensional array of complex numbers. So you might just, you might want to view this not good at drawing this. You might just want to view this as like some well, you might just want to view it as a three-dimensional array of numbers. No, well, I'll draw some ones later, some better ones later. Okay, I think it's hopefully clear. So let's do an example where this three-dimensional array is easier to draw. Namely, let's take C to be 1. Okay. So the last space is just one-dimensional, and then T looks much simpler, because then T just has a Tij, right? And here I have tensor, and then it's always like E1, right? There's nothing really happening here. So T is just a matrix in this case, right? So T may be regarded as a matrix, Tij. Right? So this is like T is a matrix. Tij, EI, tensor Ej. And of course I'll start dropping, I'll just start dropping the indices A and B for the basis vectors. So that's just a matrix, and we could ask ourselves what are the properties of this matrix, and then there's of course an important example of a matrix that is the identity matrix. Right. And the identity matrix, that would just be here, Tij is a delta Ij. Right, in this case, actually the physicists like to call this the Einstein-Podolsky-Rosen state of dimension D, say, or dimension A. Let's put it here when A is equal to B, and that's just the matrix I, EI, tensor EI. Okay. Well, that's a very important example. People in computer science really call this just the identity matrix. They will just say identity matrix on A, right? Because this Tij, it's just the identity matrix. Excellent. And then it's easier for me to draw this picture for you. Right? Because it's now a matrix, and I put ones here on the diagonal, right? Okay, good. There are, of course, other examples in this matrix case that are important for us, and the next important example are it's also a matrix, but it's product states, right? So if my T is of the form alpha tensor beta, where I write alpha as alpha I EI and beta as sum over beta I, beta j, EJ, then of course my T will be just the sum over alpha I, beta j, EI, tensor EJ. Okay? And these here are products, or these are rank 1. Right? Or they correspond to rank 1 matrices. Okay, that's the matrix case is an important example, even though it seems so trivial for the moment, but it will turn out to be extremely important in the remainder and also in the analysis of more complicated multi-particle entangled states and their understanding. So the next case is question. Sorry? Yes. Yes. Um, yes. So just think of this matrix here, right? Tij, right? So if you think of, so in general, this tensor here, or this, I like to call it a matrix because I could put a dual here, wouldn't change much. But you can think of, but if you expand it like this, right? You see Tij, and that's the matrix that I'm writing down here. And if that matrix is just the identity matrix, then the corresponding T is just the sum, right? It would be delta ij, it's EI tensor EI. And then people in physics like to call this the Einstein-Podolsky-Rosen state of level A. Okay, sometimes people only do it with or maximally entangled state of dimension A. That's not the density matrix. That's right, that's very important. This is not a density matrix. Actually, density matrices will not show up for a long time now. Okay? So these are just, I'm just talking about pure states. Okay? Just plain good old quantum mechanics of three particles, pure states, and I'm writing it like that, and then I discover, oh wow, I can write it as a matrix. Right? A two-particle quantum state. This corresponds to this two matrix. Is that okay? Yes. So Einstein, Podolsky, and Rosen in the 30s they investigated quantum states, and they wanted to understand like their curious kind of entanglement properties. And actually they had a slightly different state, but it's sort of nowadays we like to call the state that's in a superposition of two products, so E0 or E1 tensor E1 plus E2 tensor E2. We like to call this an EPR state. Yes and no, it's more like a, so if you think of A equal 2 for the moment, so let's do the example where A is equal to 2, then the case, then here we have the, in the case A equal 2, then we have the state E1 tensor E1 plus E2 tensor E2. Okay? And now if I were to relabel my basis and send E1 to minus E2, you know, I could do that. I can just relabel them a little bit, and then I get the minus sign, and it's more like the singlet. When people talk about the triplet, yes, we up plus down down. That would also be okay. But it's a specific one of the triplet states. I think often when people talk about the triplet state, they kind of mean like the mixture over the whole subspace. And then it could also be not entangled. Yes. Very good. Are there more questions about this? Yeah, it's unusual, I think. I mean, if you haven't thought about these states as matrices yet, not so. Yes, deliberately. Yes, yes, I'm we could. I mean, yes, I'm writing T in this form, and then I'm just looking at this matrix. Okay? Yes, no density matrices here. Yes, absolutely. Yes, that's right. It's not a problem. I mean, it is also basis dependent. I guess the definition of the EPR state. Right? I mean, otherwise, I mean, It is basis dependent, yes. That's okay. Yes? Yes. So why can I do that? I because of this, there was this question about the basis choice just before. I could choose on one of the systems a different basis. So I just, if I were to, if instead of doing this choice here on the second system, I would flip the notion of 1 and 0, of E1 and E0, and I would put a minus sign somewhere. I would obtain I could rewrite this as this one here. Okay, so in this specific case, it's a choice of basis. Oh, it's wrong. You mean I have the index? I got the index wrong. Yes, thank you. Thank you very much. I got the index wrong. Sorry. More questions? Okay. Excellent. So I do fire if something is unclear with the notation, because we will have to use it the whole time. And so let's go to the next case, which is the next difficult case, is where C is not equal to 1, but we put C equal to 2. But then, to make our life easier, we put A and B also equal to 2. And that's sort of like the next complicated case after the matrix case. Seems very familiar to us. What is that? So here I can now try to draw my picture of a cube. Okay, so it's maybe I draw the other one in a different color. I can try. I don't know. Okay. So this thing basically has it's not so great. My I can put some numbers. So this should be like it's a 2 by 2 by 2 cube, and I can arrange my numbers in this 2 by 2 by 2 cube, right? So there are 8 numbers in this case. Right, I have T, I, J, K, but now all the numbers run from 1 to 2, so there are 8 of those. I can ask myself, what are interesting examples? So I could, for instance, look at this to make my life a little easier of drawing this cube. I could say, well, okay, so let me now fix the last index to say 1, right? And then I just have a matrix. Right? So it's like, say, it's one of the 2 matrices. And so this would be this here is the K equals 1 matrix, and then I can, and this here is the K equals 2 matrix, right? Just to draw this cube. And then there are 2 well, there's an interesting example, and that interesting example is 1 0 0 0 0 0 0 1. Okay, so it's basically like, if you think of this in terms of this cube, it's the ones on the diagonal. Okay, on the main diagonal I have the ones, and if I put the 2, right, if I put those behind each other, then it just looks like that. So what is this in our notation? Well, this would be T would correspond to E1 tensor E1 tensor E1 plus E2 tensor E2 tensor E2. Sure. Some of you have seen this already. You know what it's called? Its state. I hear GHZ. Yes, it's the so-called Greenberger-Horn-Seilinger state, the GHZ state, which is a three-particle state which has some peculiar entanglement properties. And maybe a more normal notation for people in this, would be to write it down as 111 plus 222. I think that maybe in the Braquette notation, that's what some of you have seen already. I'm using just that notation. But that's a GHZ state of 2 levels. Just about 3 particles. So I will discuss everything I do today on 3 particles. We can also do it for more particles, but it will just make the notation more complicated. And most of the statements generalize to K particles that element. But yes, just talk about this is just the 3 qubit. Yeah. Well, people call it if you have many particles, then people call it the Schrödinger cat state. And then some people that manage to do it in the lab now would say 1,000 particles. They call it the Schrödinger kitten state. And if you go down, and down to 4, I don't know. I call it the 4-particle GHZ state, but we should call it the 4-particle kitten state. All right, this is an interesting state. We'll look at it a lot more in the algebraic complexity or in the computer science literature. This thing here has maybe a more down-to-earth name. It's called the unit tensor, in analogy to the unit matrix. That is the EPR state, right? That's like a unit matrix. This guy here is a unit tensor, so people will call it the unit tensor. Okay, so there's another example here. Yes? Yeah. Yes, you can have that as well. So you mean like I could have this one where both of them are the same matrix? Yes, we could have that, and this would be another good example, okay, for the same format. All right, we could take your example, which is what about putting 1 0 0 0 here, and here we put the same. All right. All right, that's your question. Yes. So this one actually will be very similar to this matrix case over here. And why is that? Because if I write down what this means, it means that I have E1 tensor E1 tensor E1. That's this slice. We call it a slice actually. Plus, and then the second one is E1 tensor E1, right? For this one, tensor E2. And that one I can write as E1 tensor E1 plus E2. Hold on. E1 tensor E1 tensor, and then I can put it here as E1 plus E2. All right. Okay. So that's an example of it's actually an example of a product tensor, right? Some people call it simple tensor or a product quantum state or an unentangled quantum state. But I think product is sort of like more immediate than starting to call it unentangled. Okay, good. I'll move over to this blackboard again. I have another one. I have another example for you for this 2 by 2 by 2 case, which is very famous as well. And that is the following. So if you like this matrix notation, let me start with that. Okay, so it's a 1, 1. Let me see that no, I want to have them here. Sorry for this. Okay, so yeah, and if I write down this state here, then my tensor just looks like E1 tensor, right? So the last index here is k equal 1, okay? And here the last index is k equal 2. So in the k equal 1 case, I have E1 tensor E2, that's this one here, and I have E2 tensor E1. And for this one here, for the k equal 2 case, I have E1 tensor E1, right, tensor E2. Okay. Does anyone know what this is called? The W state, yes. So people call it the W state. So let me just put a W here. So that's a W state. And we'll learn later more about the relation of these states. There is a reason for why they got these names. In regular notation. In regular notation, yes. I like this. This is a good question. This was a good question. Okay, so all right. I can convert everything into regular notation. Okay, so there is 1, 2, and the rest is 1s. And even more regular would be to start labeling the bases from 0, right? From 0 to 1. But I'm doing it 1 and 2. I'm sorry, I had to do a choice at some point. That's how it is. Okay, good, excellent. So that was my W state for you. What happened here? Did I not pull this up? Okay. I just want to use that blackboard really. Dangerous here. Very good. So okay, so these are maybe like the standard examples that you've seen. Now I want to come with an example that seems very familiar, maybe. Somehow it's maybe not. So, and that's the following thing. That's the following example. And this is the example of computer science. It's an example of computer science that very much relates to physics. And I want to, and somehow I think this is a very kind of like interesting connection that I've been fascinated by for a long time. And I started to harness and try to understand the connection between these two. And it's the following. So you all know this problem of like taking two matrices and multiplying them, right? So let me give you a matrix. Okay, so let's say a matrix. I call the matrix A now, not to be confused with the system name. So A is a matrix. So it's just a matrix, a D by D matrix. Okay, so A looks like this. A11 up to A1D up to AD1 up to ADD. All right. Okay, so now I give you also matrix B, all right? And what you all learned, regardless of your degree, is how to take the product of these two, right? So what you do what you do is you write down the matrices like this, right? And then you take, this is your matrix A, right? And this is the matrix with the B's. And then what you do is you multiply them, right? You take the first row and you multiply it with the second column, and that gives you an output result. Gives you a result in this output matrix, which is on the top left. Okay, and now you do it for any row and column, and this way you get the d square outputs here. And so if you think about it, if you of this product, right, you want to know the entry ik, okay, so I through k's column, then you find the formula that says it's the sum over aij bjk, okay, where the sum goes over j. Okay, that's your normal kind of way of multiplying two matrices. But if we think for a moment more abstractly about this operation, then what it does, it takes a pair of matrices and it maps it to the matrix product. And the first thing that you notice is that actually this operation here, it's a bilinear map. So it's linear in the first argument, right? Because if I scale A by a constant, then I'll just get a constant times the result from before. It's also linear in the second argument, because if I scale B, then it will also scale B. So people call this a bilinear map. Bilinear map. All right, so sometimes it's what you could do is instead of looking at the output as a matrix, you could look at it as like a bit like I did over here. You could look at it as like one output entry at a time. That corresponds then to a very related map, namely to the following map. It takes ABC and it maps you to the trace of ABC. And you notice that this map here is trilinear. So actually these maps here kind of like contain the same information. Right? You could, if you want to get a specific output entry, you could put C to a specific matrix, and this product will like give you the right entry. But this trilinear map we could write in coordinates. So we could say, well, let me write this MD. These are really just, right? MD, these are really just D square numbers, right? So live in CD square. And CD square has a nice basis, and this basis for CD square is given by, we could call it EIJ, but EIJ is actually like EI tensor EJ. If you want, you could put a little dual here to indicate that you were talking about a matrix, but we could also just think about it this way. So then you write this map in coordinates. Okay. So it takes, it's a map, and I like to call this map, I'd like to call this map MAMU for matrix multiplication. Okay. All right, so what does MAMU do, right? So MAMU, I got so used to it, I can't laugh anymore at this. So, so MAMU is now this map. So MAMU is now this map that takes you from here to here. And now we want to write MAMU in a basis. So what does MAMU do? I'm going to do this now in a good way. We already computed actually up there what it is. So well, I'm just writing it down, the tensor for you, or the map, right? The trilinear map is a map that associates to well, let me see if I can do it in a sleek way. So I just write it down for you, and then we can discuss it maybe. So it's the sum over ijk, eij, tensor ejk, tensor eki. Okay, so it's I want to look at this particular object. Okay, so I'm defining Mamu D as this way, where all the indices go to D, and I'm claiming that there's something that lives in CD square, CD square, CD square. And now you see when you if you were to contract this with your matrix A, you contract this with your matrix B, then what would come out is exactly what would come out here is exactly the matrix C, and or if you also contract it with this matrix C here and then take the trace, this is implementing your map. Is it clear? Yeah, maybe I'm not doing the whole. Yes, go ahead. Yes, I do get a scalar. So if you now take so take the three matrices, right? Write them as so the way to do it, if I so one way of seeing that this is the right way, that this is the right map, is that you write your matrix, right? You write your matrix A as this sum over Aij, Eij, and now let me put a dual here, or a bra if you want. Right? And now you do the same with the B. You write it in this way. You write it as the Bij E, maybe, yeah, okay, I'm writing now with Ij, but, and then you do the same with the C. And then you see that if you take a tensor, I'm a bit challenged with these blackboards here, I have to say. I feel a bit challenged, but let's try. Okay, so now if you take A tensor B, tensor C, and then Mamu, right? So I put the duals here. Okay? So they contract with these guys here. Then what you get is, right, this one here will make sure that you have the Ij component. The second one will make sure that I get the jk component. And the last one will make sure that I get the cki component, and then I have to sum over all of them. Okay. And that is exactly the result if you take this map. Okay. So this tensor, right, written as a tensor here, can be used to implement this matrix multiplication. So this here is the map that kind of like that does matrix multiplication for you in the tensor notation. Okay. Yes. No, it doesn't matter now for the moment here. I just feel like that. I just want to bring you to the tensor, and then We'll talk about actions on the spaces a little later. Yes. 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 Right. So if I have this map here, right? If I have this map, then I can recover this one by just choosing. I choose specific C's and I get this one out. So the mapping code. Sorry. Yeah, but no. Think more of the matrices with the 1 somewhere and the zeros everywhere else. And then it will exactly give you this it will exactly give you this value here. Okay, and then you choose all these d square values, and then you'll get that, and then you'll have basically by d squared times evaluating this map here, you'll get this map back. But so it contains all the information about that map, and so therefore it's sort of like it's equivalent to considering the matrix multiplication map. So now that we sort of like seen this relation to matrix multiplication, you see we should take a look at this tensor once more. Right, so now it's just a tensor, it's just an element in this vector space. Okay, the dimensions a, b, and c are now d squared, but who cares? And these eij, they were actually made up of ei tensor ej. They're kind of like a product basis for the individual d square spaces. So let me just write it out. Right, let me write out this Mamo D. Right, the Mamo D is just ijk ei tensor ej tensor ej tensor ek tensor ek tensor ei. Does anyone recognize that object? Does it look familiar? So, is it some EPR pairs, says Graham? Yes, so look, it's EPR pairs. So if you think of these as like 3 particles, 1 particle here, 1 particle here, 1 particle here, it's like an EPR pair between the first and the second particle, and between the second and the third, between the third and the first. Okay. So this is just like 3 EPR pairs, right? Pairwise, right? And if you like graphical notation, like I do, then you might want to draw it like this, right? So okay, there is a, I have these 3 particles, and I have a d-dimensional EPR pair here, and an EPR pair is indicated with a with an edge. With an edge, and I indicate that this is like still 1 particle, 1 particle, 1 particle. Have you seen this condensed matter, people? Have they seen this tensor before? Yes? Okay, yeah, maybe more. Yes, that's probably right. It's like a little bit out of my depth, but AKLT, yes, all kind of like nice comments. It's just like a little, the smallest possible example of a matrix product state with circular boundary conditions, I would say. Or, you know, it's like it's the underlying EPR pair structure of 3 particles. Okay, but we might come to that a little more on Friday. So here's something surprising about it. Let me see if I want to tell you about it now or later. Well, let's talk more about structural properties. I'll have some more surprising things to say about this guy here later. How am I doing? So it's like 1 hour. Good. Okay, so now that we have like some examples in mind, okay, so we should have some examples in mind now. We got tensors. These are like states of 3 particles. If one of the particles is kind of like not there, or if it's one-dimensional, then it's just a 2-particle state. We can think of it as a matrix. If it's a 3-particle state where the dimensions are all non-trivial, we've seen some example with 2 by 2 by 2. Over here, we have seen the GHZ state, the W state, and then we've seen something maybe unusual or maybe not so unusual, namely 3 EPR pairs in a circle, which had this very surprising connection to the problem of multiplying matrices, namely it was a structural tensor of multiplying matrices. So now I want to turn, after these examples, again a little more abstract, and try to understand some basic properties of tensors, or some basic operations that we can do with tensors. There are 2 basic operations we can do with tensors. One of them is the tensor product. Okay. So I can give you, we can take 2 tensors, why not? T and T prime. And T lives in CA tensor, CB tensor, TC. And T prime lives in everything primed, okay? Like CA prime, CB prime, CT prime. My talk is a little short. Okay, this is prime. Okay, there's T and T prime. These are 2 tensors. Now we can take the tensor product. How do we do that? Well, we just form T tensor T prime. And obviously T tensor T prime will live in CA tensor CA prime, tensor CB, tensor CB prime. You see I'm reordering already a little bit. Tensor CC, tensor CC prime. But in the world of these tensors, I want to look at a variant of this here, which I call the Kronecker tensor product. But I'll just read. And what does that do? Well, you see, the problem here is that I started with a tensor on 3 factors and another tensor on 3 factors, and this tensor product spit me out a tensor on 6 factors. But I only want to deal with tensors on 3 factors. So what I just do is I will just put some brackets here. Okay, and I'll regard it again as a tensor of 3 factors. That's what our tensor product does. Maybe a good idea. What does this do if I want to think of tensors as these cubes, right? As these cubes with numbers in them? What does this tensor product do? Because there's another cube coming out, right? So what are the numbers in? Sorry? You have to speak a little louder. It's very high. Yes. Exactly. Yes. So you could think of that's a way of thinking about it. is that you view the first one as the coarse outer structure of your tensor, and then so you write this. You could write this in like some you write this in this in your cube form, right? Say that's your t, right? This thing is your t. And then in each of the little boxes of your t, where there's some number, right? Say the first number here was t 111. What you do is you replace that number by t111 times, or you multiply that number by the tensor t prime. Right? Of course, if that number was 0, then it will turn into the 0 tensor on that block. Well, turn into the 0 block. Okay? We'll play a little more with it later. There is actually that was the more complicated one. Now can relax. There's a simple operation we can do in tensors. That is the direct sum. This one, the complicated one, that's sort of like the one that we're used to in the lab, right? I have 3 particles, I have another 3 particles, and then I group them 2 by 2. But the direct sum is a very strange operation for physicists. But mathematically, it's much easier. So what does it do? So I again have t and t prime, the same things. And then I define t direct sum t prime. I want to have this guy lives in CA direct sum CA prime. Okay, and then there's CB direct sum. That's a direct sum, not a tensor product. CB prime tensor CC direct sum CC prime. And how do I put it in there? What is it? Well, it's just as if I had taken different bases, define this one and this one, and I just collect the bases together. So maybe the best way of viewing it is again as a cube. Right? If you think of it as a cube, then you make a new cube, a new 2 by 2 cube, 2 by 2 by 2 cube, and you put one tensor in the top left and the other tensor in the lower right. That's what the direct sum does for you. So if we can also write it down maybe once properly. So we do Pijk, we do EI, tensor EJ, tensor EK, and then we take T, and then we take a new set of Ti ijk, and then here we take EI tilde and EJ tilde and EK tilde. All right. And now how do I do this? Well, I could make I double the dimension. All right. So what I can do is I can just make a new basis where the first A basis elements, right, are these guys here, and the rest is 0. So maybe we do that. So it's like E1 hat. That's now my new basis, right? That's 1 and all the zeros all the way down. Right. So that's the same as E1 hat, and then I go all the way to, but this guy here has this guy here has there's D, right? The whole thing has 2D or 2A entries. If I do this for A, sorry, I have this for A, right? I have 2A entries, and then the first ones I take those, and for the second guy, the second entries here, I put them down here, right? So in this way, I get this 2 by 2 cube with. Yeah, well, if you put them all to be 2, right, then you get a 4 by 4 by 4. What do you mean with where 16? What do you mean the left-hand side? The left-hand side, this one here? Yes. Yes, that's right. Yeah, it's a very kind of wasteful embedding. The rest is just 0. Okay, we do a matrix example. Yeah, but the rest is zeros, right? It's a very low-dimensional embedding in a very high-dimensional space. This group, right? For matrices, so if T is a matrix, all right, and now let's take D by D matrices, and we do the same with like B, right? Then the new matrix has just the matrix up here, right? It's just T that's up there, and this one is the B. Okay? So we'll just turn into a block diagonal matrix. So it's a very simple operation mathematically, but physically it somehow seems weird. Right? So I give you a quantum state, I give you another quantum state. Now I take the linear superposition of those two quantum states. It's certainly something it's not easy to do in the lab, right? I give you a quantum state, give you another quantum state, and do the superposition of the two. There's no natural physical operation that does it for you in the lab. But it's a nice mathematical operation. All right. Maybe I start on the left again. And maybe I do a trick, which is, no, it's not a trick. Okay, so what we can do now is we can apply this direct sum. I want to give you an example of this direct sum that is maybe a little bit unusual. Okay, so here is a example. I start with a very nice vector, E1 tensor E1 tensor E1, right? And it just lives in this one-dimensional vector space. Okay, C tensor C tensor C. Okay, A, B, and C equal to 1. Okay, now I take the direct sum of this thing with itself. What I have to do then, right? I have to, right? So what I want to do is I want to say, what is this? E1 tensor E1 tensor, or let me call it T, right? We call this T. And what is T direct sum T? Can someone see that? Here's some letters there. Shout them out. Yes, that's a GHZ state. Right? Because now I have to make a 2 by 2 by 2 block matrix, and in the top left I have a 1, and in the lower right I also have a 1, and the rest is zeros. Okay, so actually this here is the GHZ state with 2 levels, right? The GHZ state. Right? Because I have to take this one, and then I have to plus, and then I have to take that one again, but I have to choose new basis vectors. And I can call them 2. Okay, that's a very funny little property. What else do I want to tell you? I have another example. Yeah, here's some other observation that's related to the tensor product. Okay, so that was for the direct sum. Let's go back to our tensor product. Here it was. Okay. Maybe we do the matrix case, or it doesn't matter. So let's take the GHZ state. Okay. And let's tensor it with itself. What's that? Now we have produced the GHZ state by this procedure, and now we just tensor the GHZ state with itself. What do I get? Yes. I get two of them. Yes. 4 level. Yes, I get 4 levels, right? So if I had the GHZ with 2 levels, right, the sum goes from 1 to 2, then if I take this one here, I get 4 levels. Or more precisely, I get 2 squared levels, right, which is GHZ4. And again, we could now do our cube point of view, right? So I take one of these identity matrices as the outer structure, and then each of the ones, right, each of the zeros, I just leave them as zeros, replace them by zero matrix. Each of the ones I replace by identity matrices, by this diagonal tensor again, right? And then suddenly I get this like bigger diagonal tensor. Okay, and if you do this now many times, right, say n times, then what do you get? GHZ of level 2 to the n. All right? Very good. Excellent. Good. Of course, the same is true for the EPR state, right? So if I replace GHZ by EPR, then it's just the same thing is true. What about MAMU? Yes. And it brings you from the A space to the A prime space, right? These are linear maps, linear. And the B from CB to CB prime. And the map C from CC to CC prime, right? So we say T is bigger than T prime, or T restricts to T prime, if there exist linear maps A, B, C, such that A tensor B tensor C, well, that's a big linear map, applied to T is equal to T prime. Okay, so basically that you can locally massage this tensor T such that it becomes your new tensor T prime. And this local kind of thing we do with linear maps. Okay? If you can do that, then we say T is better than T prime. T restricts to T prime. Now, in the quantum information context, this notion has a different name, and it has the following name. If you think of T and T prime as being quantum states now, and then instead of T restricts to T prime, people would say that T can be converted to T prime with SLOCC. Okay? And SLOCC stands for stochastic local. All right? The local is easy to understand. That's just like I do something on particle A, I do something on particle B, I do something on particle C. Local operations, okay, so local operations. Okay, and then there's some weird part, classical communication. Okay, so basically, local operations you understand. This is clearly something we can do locally. Stochastic means the fact that really we don't care about the length of the vector. So we don't care about the length of this t, okay? So if I never care about the length of t or the length of t prime, then I kind of threw out probability in the bin, right? So it's like looking at the quantum mechanics textbook and forgetting Born's rule. Right? And then suddenly, if you do that, then you can convert t to t prime with these local operations. And because you don't care about the probability, you just call it stochastic. Okay? And then you can, this classical communication is a little bit less relevant. So it came from this connection to LOCC. I think Fernando probably told you about LOCC. Yeah? You all know what LOCC is? It's very complicated, right? So LOCC is very complicated. And LOCC on 3 particles is even more complicated. So what we're doing here is we're making life simpler. We're saying, forget mixed states. We just play on pure states. But then forget the probability of success. We're just happy if the probability of success is non-zero. And then life simplifies. And these ABCs, they're kind of like your cross operators that Fernando, I'm sure, told you about in LOCC. Okay? So they're your local cross operators. Yes. Exactly, yes. That's what you do. Right? So you can do what you can do in your lab is you do some unitary operation, right? You switch your apparatus on, you do some Hamiltonian, you rotate it in some way, then you partially measure your system, and then you post-select on some particular outcome that you got, say 5, all right? So your display shows 5, you say, okay, my display showed 5. In that case, I only post-select on the events where I have seen display showed 5. And in that case, I have produced this particular quantum state T prime. Yes, you can view it as applying an isometry plus a projective measurement where you post-select on one of the outcomes here. And that connects you to here. This notion of restriction, that's why I use this language, is though much older than SLOCC. So people have studied this. In the 80s, it got the name restriction, and probably people have studied this earlier than then already. No, these linear map here are your cross operators, right? So if Fernando told you that on density matrices, you see these are all vectors. I'm not making density matrices out of them. Right? So on density matrices, you operate with completely positive trace-preserving maps. For those, you have a cross representation. Cross. Oh, Fernando didn't do it. Okay, so I'll write it down. All right. So if you have a density matrix, that's now a matrix. Well, that's yeah. Okay. So then you would operate on it with this with a completely. So this is density matrix. Density matrix. This here is a quantum channel. Quantum channel. Quantum channel is a completely positive trace-preserving map, right? And this has an cross-operated sum decomposition, some I, ki dagger, okay? And now imagine that you're doing this map on you have one particle, okay? One particle only. You have one particle only, send some quantum state, you do this operation on it, and now this cross operator sum decomposition you can also interpret as getting result I, okay? Display shows I, and condition on the display showing I, you got that as your post-measurement state. If you're in that situation, and if this rho actually was a pure state, right? Say a state V, right? here is the bracket notation for the state V, then it would look like that. And then you see that what it says here is just upon post-selecting, I received outcome I. It's just as, you know, as I apply K to V, and this is just the Hermitian conjugate. Okay? So if I'm in pure states and I act with cross operators on them, and I post-select, and I get a pure state again, and it's just like applying a matrix to my vector. All right? And if I now have these LOCC operations, and I do the same, then actually I get a triple product of 3 cross operators. And these 3 cross operators, I just call A, B, and C here. But you can just do it locally, right? You do your local map, you do your isometry, you do a post-selection, and this combined thing of doing the isometry and your projective post-selection, that's your map A. Okay? Your linear map A. Yes? Yes, but I'm just bringing it back into the quantum realm. It's just to connect it to quantum mechanics and how you would implement it in the lab, right? And when I connect to the quantum mechanics and implementation in the lab, I need to bring in the tensor product. Graham's telling me I have 0 minutes, right? So I have to bring and I have to tell you how to do it in the lab. And what you do in the lab is you choose some Hamiltonian, you do some time evolution with that. That is a unitary or an isometry, and then you evolve it with that. And afterwards you do a measurement, which is some projective measurement. And then you have the composition of these maps, and they will give you this, right? It never kind of hurts to have the inner product in addition. It's just that often we don't need it.